Hi, in this video I will show you how to use phase shifting matching network designer. Okay. So, this is the zip file. So, here if I extract this, so let us extract the file, let us extract here. So, it will take some time. Okay, it has been extracted. So, there it contained one folder phase shifting mn or basically phase shifting matching network, and another file is basically load to S1P file. So, its content S1P file or basically a load file, that is the S parameter of a one port network. Okay, so let us go to the application window. So, here it is difficult to search. So, here, so phase shifting MN. So, this is the application. Okay, so if you double click on it, then it will take some time to load. Okay, so it has been loaded. Okay, so a window will appear. Okay, so this window will appear. So this basically introduce the concept of you can say utilizing the phase shift, basically how to design a matching network using considering the phase shift. Okay, so in a typical matching network, S11 should be ideally 0 and S22 also should be 0 and S12 and S21 should be 1, the magnitude, and the phase shift is basically written by the phi. Phi is the amount of phase shift. So, when the signal travel from port 1 to port 2, so the signal will get a delay of phi. Okay, so I will give you the details that what is actually this phase shift physically mean. So, it is basically the phase shift of the Thevenin voltage source, which has been introduced in the paper. Okay. So, we have said that it has been already said that frequency is in gigahertz range. The Z0, so please note that this Z0 is basically the reference impedance, not the port impedance. Okay, so this Z0 is the reference impedance. So, port impedance are basically ZS and ZL. Okay, so source impedance and the load impedance. So, if I choose the topology as let us say a lump pi network. Okay, and here please note that say here two options are there. I can choose constant load or frequency dependent load. So, here I am choosing basically constant load. Now, so some of the most of the values are basically already filled, or you can modify it according to your whatever you are trying to design. Okay, so for in this example I will show you how to design a matching network which matches 50 ohm load to 100 ohm source with a phase shift of 90 degree, because it is a very well known thing that basically quarter wave transmission line of characteristic impedance 50 square root 2 or basically 70.7 provide a phase shift of 90 degree. So, that is basically a well known example. So, that is why it basically load the initially this kind of you can say configuration or basically design you can say variable. Okay. So, here I am choosing the number of section is 1. So, I will show that multi section also later on. Okay. And another thing is that this element of the matching network I have considered as lossless. So, this is basically series reactance and these two are shunt susceptance, and this basically represented by some either capacitor or inductor depending upon the whether it is positive or negative. Okay. So, that thing. So, how you can do the design, just you need to trace the design. So, that is it. Okay. So, design is done. Okay. So, this is your source and it has a source impedance of 50 and this is load, the load having the load impedance of 100. So, I am not writing because sometimes that for the frequency dependent it is quite difficult because that for the frequency dependent that load is basically function of frequency. So, so that is why I have not written in the you can say in the in the application that what is the load source impedance and what is the load impedance. So, you can understand from this. Okay. Now, this is the basically the designs, okay, or the circuit. So, you can see, so it is basically as we know it is basically equivalent to a symmetric quarter wave length transmission line of characteristic impedance 70.7 ohm. Okay, and quarter wave length means basically 90 degree transmission line. So, this 90 degree. Okay, this is equivalent. Now, what is happening here? Okay, so there are two phenomena is occurring here. The first phenomena is the load, okay, so the load transformation. So here is the load, so you have a 100 ohm, okay, so here it starts from here, so here you have a 100 ohm, okay, and through this capacitor, this 100 ohm is transformed to this impedance. So that is 33.3, it is the real part, and the imaginary part is basically minus J 70, sorry, for 47.1. Then this inductor is basically converting this impedance into this one, okay. So that is 33.3 and 23.2, and then finally this capacitor is converting this impedance basically into 50 ohm, okay. So this is basically converting the impedance into 50 ohm. So in this way total impedance matching is occurring from the load point of view. Now what happened into source point of view? So that things can also be shown through this application. So from the load source point of view, so we start from here, okay, start from here. So here if I, okay, so it is not pointing out clear properly, so into the so here we started from here, it is 50 ohm, and then we are basically converting this 50 ohm through this capacitor 2.25 picofarad, okay. So through this capacitor we are converting this into this one, so that is 33.3 minus J 23.4 ohm, and then this inductor basically converting this impedance into this one, okay. So that is basically 33.3 plus J 47.1, and then finally this capacitor is converting this impedance into 100 ohm. So that is the thing happening, okay. And if you want to visualize both the source and the load transformation simultaneously, you can see that also, okay. So here two phenomena is occurring, so that is one is basically source transformation, so it started from here and this goes to here and then goes to here and then finally come to here, so that is the source transformation. And in the load transformation it started from here and goes to here and then goes to here and then finally come to here, okay. So because here the equivalent load I will see as 50 ohm and here the equivalent source I will see as 100 ohm, okay. Now the same phenomena we can observe in the Smith chart plane also. So let us see. So in the Smith chart plane you can see, so it has been started, so for the okay, so let us start with source transformation. So source started basically it is 0 point, so and then from here via this capacitor it convert to here this point and then it convert to this point and then finally it goes to this point or the 100 ohm, okay. So this is the thing happening in the Smith chart plane. So basically it is nothing but basically a transform domain, okay. So basically whatever we are seeing in the load plane, so it is basically or the impedance plane, so that has been transformed into Smith chart plane, okay. So it's in the Smith chart plane everything is basically within plus minus 1 in the x side and the y side is plus minus 1, it is basically in the reflection domain sometimes we call it, and everything is normalized with respect to this 50 ohm, okay. So that is the thing, okay. So next is basically you can see similarly the source load transformation also, so this phenomena, and you can simultaneously see the source and the load transformation. So in this way it is happening, okay. So this is the source transformation and this is the load transformation, in this way it is occurring, okay. Now come to the analysis, okay. So if I put just press the analysis, I do not need to put this f min, f max, so the software will automatically take some value, and if you want to give you of your choice you can do so also, okay. So let us press the analysis button, it is done, okay. So at the design frequency it is matched, perfectly matched, and you can see that S21 is almost 0 dB throughout this band, and if I want to see the analysis over a long range, we can see that also, that 5, let us choose the maximum frequency 5 gigahertz, and this is 0.01 and this is the delta f, or basically the gap between two successive sampling point. So here lots of samples are there, frequency sample. So if I put the analysis, now it will show. So, this shows that it is perfectly matched at the design frequency, and you can see the phase also. So, because I have designed for the 90-degree phase delay, so it should show a minus 90-degree phase in the basically in the design frequency. So, let us see the phase. So, for seeing this in a more close way, so I will zoom it. Okay. So, let us zoom it, and then finally if I click on it, so I can see that at the design frequency it is providing exactly minus 90-degree phase delay. Okay. And you can zoom out and see it also. So, these are the features available here. Okay. So, you can see that it is providing a phase delay of 90-degree. Okay. And this is the amplitude response, and you can see that it has a quite good matching bandwidth over this band, and you can see the actually the what is the response. Okay. The next thing is we will consider a complex load instead of a real load. So, let us consider that I want to match a impedance of 75 plus. So, here instead of j I will write 1j, because it is a common Python way to write the imaginary number I or j. Okay. So, 1j into let us say 30. Okay. So, this is 75 plus 1j into 30. Okay. So, this is the impedance. So, let us press the design again. It is design. Okay. So, let us move to the impedance plane, because in the impedance plane everything is more clear. So, let us say that the source or the load transformation. So, load transformation basically start from here. So, you have 75 and 30, and it basically converted. So, basically through this capacitor it converted to here, and then through this inductor it converted to here, and then finally it reaches to 50 ohm. Okay. So, if I press it, okay, so you can see. So, it is basically converted to 50 ohm finally. So, in the same phenomena you can see the from the source perspective also. So, it starts from here, and then finally it is the complex conjugate. Please note that. So, here whatever the load impedance, it is basically complex conjugate. Equivalent source impedance here is basically complex conjugate of the load impedance. Please note that. Okay. Okay. So, the same thing basically I can see the both source and load, and it is basically obvious that they are basically complementary. The source equivalent and the load impedance equivalent are basically complementary to each other. Okay. This is done, and then I will show you the lossy case. Okay. So, if I want to design a impedance matching network that these elements are lossy, so what will happen? Okay. So, let us put they are lossy. So, these loss are basically represented by the Q factor. So, typical Q factor is basically for the good design is basically 200 or let us say very bad, little bit bad design of 50. Okay. So, I can redesign it. So, please note that in the Q factor, if I include this Q factor, so what will happen? So, this inductor value, then this capacitor value will remain unchanged. Only thing is that in the series element an additional resistor will be added, and in the parallel element additional basically parallel resistance will be added. Okay. So, if I do the design, so it is the thing. So, you can see here. So, here in case of lossy case, so they are not complementary to each other. So, this source impedance equivalent or the load impedance equivalent are not complementary to each other. So, therefore, they are not perfectly matched. Okay. So, at the design frequency it is not perfectly matched. So, however, I can compensate this using let us say some kind of how can I say I can compensate this using some additional reactive element. So, in that way I can do a good matching, but one of the thing is basically you need to consider the transmission amplitude. Okay, the transmission amplitude we cannot make it 0 dB. Okay, or basically the insertion loss is less or insertion loss is more than 0 dB. Okay, insertion loss that is basically 1 divided by S2 watt. So, that is basically more than 0 dB. Okay. So, you can see here, so it is not perfectly matched, okay, from the graph itself, because to be perfectly matched, that load equivalent, okay, so that load or the source equivalent at the load point. So, this is the source equivalent at the load point. So, it should be ideally 75 minus J30, but here it is showing 72.7 J30. So, this additional thing can only be compensated through additional transformation. So, this can only be compensated through additional compensation, okay. And you can see in this this thing in the basically load point, okay. So, basically the load at the source point, the equivalent load impedance is supposed to be 50, but due to this loss element I am getting a 52, and this is coming as 0.4. Okay, so, I am getting some you can say some additional thing, okay. So, additional thing in the you can say the resistive part, okay, the 2 ohm additional thing. So, that basically leads to some kind of losses, okay. So, I will show later on that what is the effect of loss in the analysis, okay. So, let us do the analysis. So, you can see, so it is not perfectly matched. So, as I told you that there is a deviation between the what is the conjugate matching and what actually you are getting due to this additional loss. So, it is not perfectly matched, but it is good matching, okay. We can say it is good matching of 35 dB. So, that is good enough, and but the one thing you should notice here, so that is basically the amplitude of S21, okay. So, you can see here the amplitude of S21 is basically minus 0. You can say 0.3 dB, okay. So, let us click on it. So, you can say minus almost minus 3. So, this is ideally it should be here, ideally for a perfectly matched it should be here, or even if I try to do some due to using some extra you can say inductor capacitor, if I do the exact matching, still I cannot get exact matching. So, sorry, it means basically S21 is equals to 0 dB, okay, or basically full transmission, or S21 is equals to in the normal scale 1, I cannot get, because of this lossy element. Some of the power is basically getting dissipated across this loss element or this resistor, okay. So, so that is the thing from this perspective, and you can try some other matching network also. So, let us make it again lossless, and let us design a T match network. So, instead of 90 I will design for let us say 30 degree, okay. So, let us design it. So, you can see, so this is the T match network, and in this way this transposition is happening. So, it is a very nice looking graph, and you can see the analysis result. So, this is the analysis result, okay. Okay, so that is fine. Now, the thing is that we will try to make some other kind of matching network. So, for example, let us say I want to design some multi-section matching network, okay. So, the multi-section, the advantage of multi-section matching network is basically wider bandwidth, okay. So, I will use the pi topology, and let us same 50 to 100, and instead of 90 I will use 590 degree section, or basically 580 degree section, 400 is the phase shift. 400 means each section provide 80 degree phase shift, okay. And then it is in section is 5, and then design, this design, okay. So, this is a very nice looking graph, and it shows very symmetric, because it is lossless. If it is not if it is lossy, so in that case this symmetry become it is not remain, okay. And if you do the analysis, you can see it is providing a very good bandwidth over the band, okay. So, it started from here, and here you can see, so it is providing a very good bandwidth over this range of frequency, okay. So, you can see here it is providing a good. So this can be adjusted. So this here you have a certain peak which is more than 10 dB. So that can be decreases by changing this phase. So here I am basically utilizing the phase as the basically design variable instead of utilizing the exact phase, because one of the fact is that we basically want the phase difference, not the absolute phase. We basically want the phase difference, not the absolute phase. So if I put it as 450, so let's see what happened. Like again design it, I think design done, and then do the analysis. So still it is a little bit off. Let's make it 500. Design analysis. So it is basically a little bit down. So now it's fine. It's quite good over this band. It's quite good. So, and you can clearly see that 1, 2, 3, 4, and 5 regions are there because it is 5 section. Okay, and you can see that you can basically designing the basically wideband impedance matching network using this technique. But please note that this ripple are basically we are not exactly defining that where it should be the ripple and how it can be controlled. So that is we are not doing, but by changing this 5 variable and the number of section and this thing, we can basically control it. Okay, so that is a little bit heuristic method, not exactly deterministic method. Okay, so next is this is done, and next is the same thing we try with T topology also. So let's see that whether it can be done or not. So instead of this, I'll choose 500, and then instead of 1, I'll choose 5. Let's design it again and do the analysis. It is almost having similar kind of phenomena. Okay, so we are getting a quite good bandwidth over this thing. These are the component value, and you can simulate this using some other circuit simulator like ADS or let's say ANSYS designer, and you can check that whether this analysis results are correct or not. Okay, so that can also be done. Okay, because it is providing the exact value, and so I am sticking to 1 gigahertz frequency. So you can change the frequency range also. So let's say instead of this, let's do it at 1.2 gigahertz. Design analysis. So you can see, so it is basically coming at 1.2. Okay, so 1.2 it is basically designing, and everything is shifted. So you can design for 2 gigahertz also. To design analysis, so you can see it is basically shifted. So everything is basically why, because as I change the center frequency, that overall bandwidth has become increases. So it is obvious. Okay, similarly you can design for 500 megahertz also. So it's totally up to your choice. Okay, so this I have shown you this configuration. Another configuration I would like to mention, that is basically instead of constant load, you can define your load. Okay, frequency dependent load. So that is basically defined using S1P file. So if you have an antenna or let's say amplifier, and you can generate that S1P file through whatever the simulation software you are using, and you can feed that into the software, and you can design the matching network for that. Okay, so here what I am doing, so I am basically importing this file. Here you can see that I am loading this file. It has been loaded, and let's choose the frequency in megahertz range, and the source impedance is still 50, and the phase shift we are choosing 30 degree, one section. Design, it's supposed to give some warning. So it is in gigahertz. Okay, so do the design T match network. So T, let's design for pi match megahertz. Design something is wrong, gigahertz, and here you can see if I put in 30 degrees the phase shift, because this is the example provided in the paper, and let's do the analysis. So in this way it is basically transforming from 50 to this point, and if I do the analysis it will give me the analysis result. Okay, and let's see the phase that is providing that the desired phase shift of 30 degrees. So you can see here it is providing 30 degree. Okay, at the if I zoom it and then I can show you the exactly what is happening. And now instead of one section, if I design for the same 30 degree with 3 section, it can provide a little bit better bandwidth. And please note that it is a frequency dependent load. And let's see the design, and if I do the analysis, so this is the analysis. Now the lossy case also be simulated, so let's say this is the lossy case. This is 50 is the Q factor, design and do the analysis. Okay, so that's it. Okay, so I hope you have enjoyed this video, and if any bug is there in the code, please let me know, and if you click on it, it will goes to my website Scipy Code Design Lab, and so this paper is basically under review, and when it will complete I'll release the all the basically the binary version or basically binary distribution of this code or of this software. Okay, thank you.